And now we get a presentation from a slightly different research direction in our team. Dr. Li Ping has graduated a while ago on the topic of digital image correlation. He studied a DIC system that was as simple and still flexible and accurate. It only uses a smartphone camera and a set of mirrors. Nurlat will be presenting his work. Nurlat took over this research since Li Ping started working at the Beihang University. And it is in our lab very important to have somebody working and having knowledge about DIC. It's very handy for all other users in the lab as well. So Nurlat, go ahead.
Good day to everyone who gathered here. Today I'd like to show a presentation on the ePoster about smartphone-based single camera stereo vision. This work has been authored by Li Ping Yu. First of all, the stereo digital image correlation, also known as 3D DIC, is basically a technique that can accurately measure full field 3D shape and deformation. And later on, we can always extract displacement and strains inside the region of interest. However, most of the traditional commercial uses worldwide in the field as well as lab settings have several drawbacks, such as they can be expensive, they have a very high weight or bulkiness, as well as there is also a high degree of complexity in experimental setup. On the right, you can see a typical solution by the correlated solution VX3D. So in order to alleviate these kind of issues, we propose to reduce this system to a smartphone camera level. This allows us to create a very cost-effective as well as very portable and lightweight solution for 3D DIC. In order to construct this system, we only need a generic smartphone camera as well as an attachment that uses 4 small-scale planar mirrors. These mirrors are supported on the 3D printed shell and mounted on top of the smartphone tripod system. How the system works? So the main idea behind this mirror adapter is that it allows us to view the surface image of the test subject from different configurations. Each of those configurations contains 2 views of the object surface. Then a series of images of planar calibration target, as you can see here, I think here, yes, are placed and translated and rotated slightly so in order to calibrate this whole system for virtual stereo vision, basically. Then both images are separated on the left and right images. From that point on, we can match points from the left and the right and between state 0, so the initial state, and all the states that follow after. Afterwards, we can subtract the matched points between state 0 and all other states in region of interest in order to retrieve our 3D coordinates of the deformed states. This allows us to capture the 3D full displacement fields of the deformed states. In order to validate this whole system and this whole idea, we have performed some validation tests. For example, on the images C and D, you can see that we can trace a speckle pattern on the planar surface. We can measure in-plane translation, which can be measured by any 2D DIC, but also we can measure all out-of-plane translations, which are the key feature of the 3D DIC. Moving on to the more interesting cases, we also measured on the cylinder and bottle surfaces. And it can be clearly seen that the reconstructed 3D surfaces on the cylinder and surface are clearly match the real-life examples. Then we measured also using a physical caliper, the diameter of this cylinder here. And we found out that the difference between 2 diameters was less than 2%, what was 1.64%, which shows us very high accuracy of the system. Another application of this system in our lab can be used for the tensile test of a carbon fiber reinforced polymer. Here, it's under tensile load, and we can find out its mechanical properties such as elastic modulus and as well as Poisson ratio. Using conventional strain gauges to compare with our data from the 3D DIC, we have found out that the difference between the measured mechanical properties here and from strain gauges are about 1%, 1.03 and 1.04%. Most of the errors here can be attributed to the fact that the camera system is very small, and this compactness leads to thermal instability inside of the camera setting. then it allows us to see a virtual strain when there's basically no strain in real life. As you can see here, when we see some deviated strains from the real measured strain. Lastly, we also performed some shape and radial measurements of the ball that has been fully puffed up with air and then slowly deflated using a needle. Here you can see the shape and radial changes over time. And you can see that the camera system perfectly allows to capture its shape profile change as well as its radial change. And the measured diameters during the deflation process, as you can see here on the bottom right, accurately shows a gradual slow change in volume. And we can also see how at each point the measured diameter. The measured diameter using the vernier caliper at the two states here and here was at the margin of error of 0.6 and 0.4%, which is very low. Henceforth, we can conclude that this kind of system is very effective in measuring both shape and motion deformation. And it has a very significant benefit of being lightweight, being compact, and does not require a huge, costly experimental setup. And it has been proved upon the measurement of the mechanical properties, as well as capturing the motion of the sphere. This concludes my presentation, and I'll be very glad to answer any questions that you may have. Thank you.
Thank you, Nurlat. Professor
Sorry, I was just
Fernando
waiting
has
for
a
somebody
question.
else to do a question. What strain rates can your system cope with? You showed us a tensile sample. Is
Yes.
the fastest rate you can test the sample and acquire the data?
Oh, that I wouldn't know. Sorry, that I
Okay.
don't know. Sorry.
Okay.
Have you been limited by the deformation rate in your measurements before?
Not really, because the capture time of the specimens were like 2-3 hours, so the strain rate was very slow, and we are not doing high-speed capture.
Okay, thank you for answering our questions, Nurlat.